This is not conjecture. We're not being opinionated on this, saying, we're making this worse. We think. I mean, it's a thing, and so, mitigation is an interesting engineering problem, right?
Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. Christopher Balhuis, we are talking about flash floods, and this is a topic that is relatively somber when it comes to geology. It's hard to have a lot of enthusiasm when we're talking about such devastating events, really. But there is some really interesting science involved in the geoscience of them, and it's really important. Like, this is one of the topics that I think when I'm teaching like an intro level class, this is one of them that's like you are going to, students sitting there, even if you're not going to be a geologist, you're going to have this influence your life in some way, shape, or form. Flash floods, like they're surprisingly prevalent. And perhaps becoming more prevalent.
That's where the whole idea came from to do this episode. Was every day this summer you turn on the TV and I don't know. It seemed like, honestly, it was every day. And
summer 2025
got to the point.
Was at least a lot of flash flood devastation and loss of life in the news frequently. It did feel like a lot, and a lot of tragic events frequently over and over and over in the summertime here this past summer. So yeah, absolutely. And I think
I'm just like, doesn't that beg the question that why? Why does this seem to be, going on more often? And is that really the case, or is it just the media? You got to ask, like, is this human induced? Do we have a role in this? And that's kind of how our discussion started.
That's right. And the answer is, we'll give away the answer. The answer is kind of. Not necessarily obvious for any particular event, but on a really broad scale, yes, humans are creating the kind of setting the stage, setting the board pieces in place to make the possibility of flash floods more extreme, more dramatic. Now, that doesn't necessarily mean that any particular event that happened this past summer was humans' fault, but I kind of envision it as, the board has been set, the chessboard is arranged in a certain way that kind of is predisposed a little bit more for the potential for flash floods. I don't know if that's a good analogy or not, really. But we're going to go through a bunch of things here, Chris. And the general flow we're going to talk about is we're going to go through just some examples, really base level, what is a flash flood, give some statistics on flash floods, talk about what causes them, and then we'll get into a little bit of how the soil can be impacted by previous events, which makes them worse. So we have to talk about, how did they form? How do flash floods happen before we talk about why might they be getting worse and what are humans doing to impact the perhaps more regular occurrence of flash floods. And then we'll kind of end with that kind of a discussion of how we monitor them a little bit and some forward-looking stuff. So first of all, the events. I don't know, Chris, if you cover these when you're teaching geoscience, like the intro level class. I certainly do a couple events, like a couple key ones, and I try and bring it home to Pennsylvania a little bit, because in part, like, our textbook has a location, a flash flood event from Pennsylvania from 1889 in Johnstown, Pennsylvania, where basically a dam was built to hold a reservoir, and that dam was poorly constructed. And I think, logs got jammed up in the drainage sluice, and the dam failed. The entire reservoir gave way. The water rushed downstream, and this was a 20-meter wall of water rushing downstream, killing over 2,300 people and destroying this town of Johnstown. So that's one example. And Chris, we've talked about in the Tetons, in our Geology of Grand Teton visual podcast series, which is on our CampGeo mobile app, we talk about a flash flood event that's kind of similar to that, right? Kind of dam failure was the cause.
Yes, absolutely. This was the Grovant event, about 100 years ago, little less than 100 years ago, where this massive landslide dammed up the Grovant River, and it created a lake behind it. But this was an earthen dam that had just, suddenly been thrust in place, and this was
not engineered, really.
Not engineered, but engineers came out and assessed it and deemed it to be safe, but that proved not to be the case. And resulted in downstream tragedy. Jesse, I have two thoughts about this. One is I want the listeners to think about maybe what are the possible ways that humans could have an impact on this before we get to that. How could we possibly have a role in this, right? To think about that.
Keep that in mind, because we're going to come back to that later on in the episode. So kind of keep stewing on that. Keep that in mind as we talk through a bunch of other stuff before then. But sorry, what was the other thing?
I can't remember. I just lost the other thing.
This hamster is really falling down on the job over there.
It fell off the wheel right there. I
have a
can't
question
really
for you
remember.
Then.
Yes, go ahead. It'll come to me.
You.
I promise.
Eventually, it'll come to you.
Yeah.
God, this is just ridiculous. I mean, this is becoming a more frequent occurrence, Chris. I don't know what that means, but
stop. That's not true.
I know,
Jesse.
floods.
I know. Hold on. I know.
Okay, all right.
My other thought is that this is actually a question to you. This is not really a traditional part of a intro level geology course, geoscience course. It's just like a section devoted to this kind of thing. And I really have a problem with that. Because I think that we need to evolve in the geoscience field into things that are more relevant than the old school kind of thought. And this is something that is important. It is something that we do play a part in and that we can then mitigate. And so that was my thought, is that it's not a dedicated part of a traditional class, and it should be.
I hear you. I just, whenever this stuff comes up, I tend to think, okay, well, what am I throwing out, to replace, to make room for this thing? And it's, I don't have an easy answer to that one. So it's definitely an important topic. Let me ask you a question here, Chris. So we're going to get to what flash floods are, sort of some definition stuff, but I think that's kind of easy. So maybe let's cover that first, and then I'll ask you a question. So what are flash floods? The name tells you a lot here. They're rapid flooding of any really low-lying area. I like this tagline: they come fast and they leave fast. That's kind of the idea. They come really fast. That's a key. Really, really fast, surprisingly fast, really hard to give any forewarning for. The National Weather Service defines them as occurring within 6 hours and usually within 3 hours of a major rainfall event. So that's what we're talking about, really quick. We're talking about hours time scale of the arrival of a flood event, usually in a stream. They're more common, but not exclusive to dry areas. And this is kind of the opposite of flooding events that we think of, like the Mississippi River, where this huge river is gradually swelling and feels like an unstoppable swelling of the river as it aggregates the water from upstream drainage things. This is a rapid pulse of water coming downstream, and it can last for a long time, but it's not lasting for a week or weeks on time. So come fast, leaves fast. My question for you, Chris, is to the causes. I think dam failure or any kind of either human-made or naturally made dam failure is a pretty obvious one. That makes sense. That's easy to imagine how you get a wall of water kind of moving downstream. If you were going to talk to students about that, would you just say that and move on? Because to me, that makes sense. Okay, dam failure, that's easy. We can move on from that. What are the more complicated ways? Because I think there's less obvious ways that these flash floods form. And so how do you go about explaining those slightly more complicated processes?
Thanks for asking that. That's a really hard question to tackle. There's no short answer to this. I guess the way that I would approach it from the standpoint of a intro level geoscience course is that, do we possibly have a role in this as humans and what we've done?
You jump to human roles.
I do,
because it makes it. You think that flash floods happen naturally without any human involvement, but do you think explaining the human impacts makes the process more understandable for how a flash flood happens?
I do. One, because it makes it relevant to them right away, and also they do seem to be dominating the headlines. These seem to be increasingly, and we looked back, and they are increasing in frequency. You and I, in our research on this, they are becoming more prevalent and more common. So why could that possibly be? You go back to one of the root causes of flash flooding is, water not being able to penetrate the surface. In other words, water running off, sheet runoff, sheet flow, getting to where it's going, the low-lying areas fast. That's a flash flood. That's the definition of it. So it can't penetrate the ground and slowly like permeate and trickle to where it's going. It's just running off like a bullet.
Ooh. Okay, this is good, Chris. So this is image number one. We're going to turn to image number one here, which is just a little GIF schematic showing what we're talking about. We've got soil here, soil particles. So these are just a bunch of black dots that represent any given soil particle, highly schematic. Basically, what we're talking about is rain falls on the surface here. Rain falls on the surface, and we're talking usually in flash flood events, we're talking torrential rain. So really, really, really intense rain. And what you're referring to as water infiltrating or water penetrating the ground, it's percolating through those soil particles. And if the thicker the soil layer, the more infiltration you can get. But there's other features about the soil and the soil surface that control how much water gets in, because any water that doesn't infiltrate has to flow downhill, and it goes across as some people call it sheet wash when it's like flowing directly across it, but it's basically runoff. It's running along the surface. It's not penetrating into the soil. And so I think this becomes a little bit more obvious. This is where we get a time lag. If it penetrates the soil, eventually it's going to make its way to a stream and flow out and down eventually, but it will take a long time, maybe make its way into groundwater channels. So that runoff is the stuff that creates the flash flood. And so I just wanted to describe that process, because we're going to talk about, that's the balance. Like that is that's the top that's spinning on edge, that we if it tilts one way or the other, we can induce a lot of runoff really quickly. So that's the edge, the kind of nice edge we're balancing on here, that trade-off between infiltration and runoff with rain coming in.
Absolutely. And then you look at, well, okay, how could humans possibly, have an impact on that? Whether when rain hits the ground or rapid snowmelt happens, where does it go? Does it run off or does it infiltrate? And so this leads us to this. Yeah.
Can we focus, Chris, on the natural factors that control this, and then move on to the human influenced aspects? Because I think some of these are obvious, some of these are not too obvious. I think so. First of all, the slope. You were couple months ago. You were at my house, and we live at the base of one of the ridges here. Not right at the base, but we're on the base, the basal slope. So like we look up one side of our house, and we have the ridge right there, and so the slope of the land, when it rains hard here, we get sheet wash down our driveway. We get sheet wash coming across the road. Like water's clearly moving downhill quick, and it's flowing pretty dang near the surface in many instances, because we have rock not too far underneath us. So the slope, this is the
I have
slope
a question for you.
Matters a lot. Like the steeper the slope, the more runoff you get, the less infiltration. That's kind of obvious. I don't know. I think that's obvious. That's intuitive. That makes sense, right?
100%. I have a question for you though. Did you consider this before you bought this piece of land, your home? Did you think about this aspect?
Well, we did we think? Yes, in a way. I mean, but we looked at the neighborhood. Our neighbor has a retention. The uphill side has a retaining pond which we'll talk about this. There's a couple of trenches that have been dug above our neighborhood that kind of funnel water sideways away from the houses in our neighborhood. So we looked at that and said, okay, this is a well-engineered neighborhood. We'll probably get some extreme flooding. If something extreme happens, we'd probably get flooded, but in normal day-to-day, normal year-to-year, probably not. So, and that's sort of the case so far. So yes, it's something we considered a little bit. Yeah.
Okay, so I think you answered my question then. Are you concerned about it with, let's say that you have a 50-year event or 100-year event, which is just the probability that you're going to get an event that only happens once every 100 years. This is a big time, thing. And you do have, or you have had anyway, I don't know if you still do, issues in your basement. So
yeah, well, before,
where does this play in?
Yeah, no, we did have installed like a French drain sump pump system in the basement, or had that installed. So because we kind of figured, yes, this is going to happen eventually.
Okay,
So yes, it does happen, right? It happens in these neighborhoods, but slope is a really big one. And the other one, the next one that I think is kind of obvious here too, is the type of soil and the soil texture, and really the thickness of the soil layer too. So how much soil do you have before you hit bedrock? What is the composition of that soil? And here in Pennsylvania, where I live, actually, there's like maybe 6 to 10 inches of soil, and then you hit a really tough clay layer right on top of that. And that clay layer does not allow water to flow along.
Is that your hard pan or not? Is that
no? I mean, it's like a thick clay layer beneath it. So I think it's actually chemically weathered, limestone and shaly stuff beneath it. But and actually, Chris, I have a funny story of this. When we started in the house, we're like, I was running, something was attached to a hose spigot that was up by the garage. It was kind of upslope, and had the hose spigot on, and for a long time for the day, I think it was running a sprinkler power washer or something like that. And all of a sudden there was like water seeping out in our yard, like down below a little bit, kind of seeping out the yard. And we're like, oh my goodness, what is going on here? This is so weird. This was tens of meters away. And so then we're like, man, this is like this water seeping out kind of right on the well line, the line between the well and the house. Like maybe there's something broken in there. Start digging down, thinking, where is this stuff coming from? Turns out the spigot has a slow leak down deep in the ground, and it was leaking, but it was leaking at an area that it would percolate up and get on top of that clay layer, and then just ride that clay layer down a pretty long ways until it hit surface, and then it would surface out right near our yard. And so you'd see the water trickling out, but it was just running under the soil, but on top of that clay layer. Mm-hmm. So that's a good example of like thicker soil means you have more ability to soak that up before it hits something impermeable down at like a clay layer or hard rock, bedrock, an impermeable surface in the ground. So
I cannot believe you just described that, because I have the exact same thing in my front yard.
Oh, really?
Yeah, I do. So I didn't have time to fix it. But yeah, I just water pools up right on the surface there. Same problem, same exact reason.
You have a hard pan layer right there.
Oh yeah, absolutely. Yeah. And it's about, my hard pan layer is 10 inches, 12 inches down, maybe.
If you go back to our hard pan episode, you'll recognize that Chris hates hard pan. It's Chris. The bane of Chris's existence is hard pan. Okay, so back to the story here. Slope of the land matters. Type of soil and the soil texture matters. Now, this is
we're talking like clay versus sand. Like that kind of thing. That's an easy example. Clay, impermeable. Sand, very porous, very permeable, and it allows it to percolate down, surface water to percolate down through the surface much more.
Chris,
readily.
I'm going to use another obvious one, the amount of vegetation. It's not quite as obvious, but I think if you just picture a forest landscape that's getting rained on, or a field that's getting rained on, versus a dry land that's getting rained on, I think you could probably imagine that the more vegetation, the easier it is to soak into the ground. Like there's more infiltration going on in those types of settings. One that's not obvious is the prior wetted condition. Describe that, Chris. Mm-hmm. What do we mean by that?
So imagine, if you will, hard pan, except on the surface. Really, really dry, almost plate-like conditions at the surface. And so when you get a cloudburst kind of event, this really short, intense thunderstorm kind of thing, because it's so dry, it's like concrete then. And it just sheds like a roof. You get runoff. You get very little infiltration. And it's interesting, if it's just like slightly wetter, there is moisture in the soil. Then you get into the chemistry of water in terms of why, if it's just slightly wet, it'll draw the water from the surface down into the subsurface and help that percolation process.
What do you mean by water chemistry? Describe what you mean. Why did you bring up water chemistry for that process?
So I think most people come across this in a biology class, which is cringy to me. But
yeah,
it's the polarity of water. Water is a neutral molecule, but because of the dynamics of the molecular structure, it doesn't behave that way. It behaves like it has an electrical charge. And so opposites attract. And therefore, this is, I guess the best way, Jesse, of maybe explaining this is that you take a freshly waxed car and spray water on it, and the water beads up, right? Water's attracted to water. And that's because of the polarity. So if you have water, hanging out in the soil right below the surface, it's going to then draw water from the surface through that and help it permeate and percolate down below the surface. And it has to do with the polarity and the electrical nature of matter. Opposites attract. Water likes water. I don't know. Water's a chemical freak. We could do an episode on that. It's.
That's right.
Okay.
And Chris, I just want to make a note here that we've talked about a lot of this stuff before in some capacity in a slightly different context here, in an episode about 2 years ago. I forget. I think we called it the infiltration game or something along those lines, right? But we were talking much about the flash flooding, this infiltration aspect, the capillary action. We covered a lot of these things. It's just this summer 2025, really hit home. There's a lot of stuff in the news, and there's some details. There's a little bit more nuance. So we're going a little bit more into the weeds here. So, Chris, okay, prior wetted condition, that matters. Like, how much water has this soil seen before? Has it seen a ton of water and it's fully loaded? Because then there's going to be a lot of runoff. Has it seen no water for a very long time? Then this capillary action won't happen, and there'll actually be more runoff than somewhere in the middle there. And, Chris, I think, this is an exercise you can do at home, right? I mean, for instance, here in Pennsylvania, it hasn't rained much at all for the last month, really. And if we go out and water some plants in our garden or something, you can spray the water on the ground and you can see it bead up. It starts to bead up right on the surface as opposed to sort of soaking in, where if you do this after a recent rainstorm, the water will just soak right in. You won't even see it, right? So there's other things that influence this. Organic material, we talked about this in our previous episode a couple years ago, how organic matter can really influence the infiltration capacity of these things. But Chris, there's another one that we'll talk about today that's relevant, which is burn scars, which was a really interesting one that comes to play in New Mexico, a flash flood in New Mexico that we'll briefly highlight. But how does this happen? How does burn scars affect infiltration capacity or the infiltration aspect?
It makes the ground kind of like concrete. You basically char the whole surface of the land, and with a forest fire, lightning strike, a thunderstorm, and so what that does is it removes the vegetation, and vegetation kind of like slows everything down, right? The root systems, the vegetation itself, the canopy, all of that slows it down. You remove that, you don't get that slowing effect. And then also just simply what it does to the surface. It greatly diminishes the permeability of the ground, these burn scars on the ground. You talked about New Mexico. I've seen this firsthand in the Black Hills, South Dakota.
Oh, is that right?
The Sturgis Rally has been upset in years past by burn scars and then flash flooding as a result of the burn scars. Yeah, absolutely.
Yeah. Interesting. Okay. Yeah. So that you create this little hard layer on top of it. The same thing as kind of a desert varnish gets created, and that's a little bit of an impermeable surface, sort of a skim coat on the surface of the ground, which then again increases runoff, less infiltration. So, Chris, I think one thing that I think we need to belabor the point here on is that the amount of water delivery in a flash flood event is usually prodigious. Like these are really, really big rainfall events that induce flash flooding in most instances. So for instance, in North Carolina this past summer, 2025, a storm dumped 5 to up to 13 inches of rain in 12 hours. That's like a month's worth of rain, or 5 times that amount.
In some areas, it's a year's worth of rain.
It's a massive amount of rain, and this creates catastrophic flooding. In this case, it fell into the Piedmont, had a little bit thicker soil, but still devastation. So this amount of rain is sometimes the soil just gets soaked up. Like it doesn't really matter whether it's prior wetted or not. It just cannot hold any more water, and so that's the end of the story. There's the rest of it's going to be runoff because that soil is completely soaked and saturated.
Yeah, that's a good point, Jesse, that I think we should add. If we were writing a textbook, we would add to the conditions that lead to flash flooding, we would add something like the thickness of the soil on top of the bedrock.
Right.
Because
right.
if you talk about what happened in the hill country in Texas, this fell on an area that is underlain by limestone with just a couple of inches of soil on top. And so there's very little ability for it to soak that in.
Yeah, and very
that,
similarly, Chris, this event was greater than 10 inches of rain in a 12-hour period. This led to tragic deaths, over 130 people killed. And the rain here kind of ran off the hillside there. So we don't just care about the porosity or the permeability of the soil. We care about how much soil there is, right? So you use the example, Chris, of sandstone in a bucket. You put sand in a bucket and you fill it up with sand, and then you pour water in it, and you can pour almost an equal volume of water into the bucket as of sand you put in there. So it's kind of 50% pore space. If you have a thin layer of 50% pore space versus if you have a really thick layer of 10% pore space soil, you don't really care about the pore space, the percentage. You care about how much total water can the soil hold. And so if you only have a couple inches of soil, that's not a lot, especially if you have a limestone layer underneath that's not soaking up anything else. And the water is just going to run right along that limestone layer and eventually come out into stream beds and creeks. And so the water runs off the hills really quickly. So the slope also mattered in that instance too, where there's steeper slopes, and so it fills up in the stream beds really quickly. And that's how you can get a really rapid, really tragic flash flood event like that. Chris, we highlighted New Mexico. The Rio Ruidoso rose heavily again because a lot of rainfall fell in this area where wildfires had previously kind of scorched the surface, and so again made this more of an impermeable layer. So I think maybe we could move, Chris, into, are they getting worse? How do humans influence this? And then also, what can humans do to alleviate some of the flash flooding events here?
Yeah, I mean, this is what led to the whole discussion that you and I had on a Saturday morning one day, sitting out on our decks, respectively. I don't see a way that we are not having a role in making flash floods worse. I just don't, to me, that does not logically make sense. We have to, because if you take, you can take a 1 mile by 1 mile area, just do a Google Earth search on any area that's been somewhat developed or really developed, and you look at all of the impervious surfaces that have been created. You look at rooftops and parking lots and roads and sidewalks and storm drains, sewer drains, things like this. So we're just getting water faster to where it wants to go. That's, I think, the huge and I think obvious way that we've played a role, but also more subtle things like just our farming practices and the act of removing deforestation and then planting on it and farming it and so on. That all of that plays into water getting to where it's going faster. So you combine all of these factors together, and that's just the obvious ways. Then you start to think about whether or not storms are getting worse.
Well, let me just touch on this a minute, Chris, because we have an example of this from 2025. Chicago had a flash flood occur in the city, and the rain event that caused that was less than half of the rainfall of the ones we talked about previously. So this was more like 2 to 5 inches of rain in a 12-hour period, but yet still caused a flash flood and a really damaging flood event because it fell on a city with, as you can just picture the city of Chicago or any big city that you can picture in your mind. There's a lot of impervious surfaces to this. So water's hitting the ground. It's not percolating into the soil. It's flowing downhill really quickly right along the surface, right? And so I think this is the sort of issue here, or how this can kind of relate to human-induced processes. What are humans doing to the landscape? As you're saying, we're taking these things and changing them and making a lot more impervious surfaces, impermeable impervious surfaces that create runoff. Sorry to interrupt there, but I just want to interject
that
example, because I think it's really interesting to compare the rainfall event that caused the flash flood, how much rain, how quickly, in these several instances, and compare Chicago to the other ones.
Yeah. So Jesse, I just I came across an article recently. I don't know, maybe a year ago. That's recent for me, but where they were looking.
You're that old. They were looking at a year ago is recent. That's pretty good, right there.
They were looking at farm use in the Mississippi River Valley. or maybe it was the Missouri. I think it was the Missouri River Valley, and how to slow down the water coming off the farmland. And they're talking about like sprinkling farm fields with the crop residue that they need to chew up and just like spread it over the farm field because they want to diminish the impact of rain droplets on the soil.
Oh, interesting.
And they're
okay.
Yeah, like so
rain,
like
the
think
physical
about
process
like
of rain hitting the soil.
Exactly.
Yeah,
and
interesting.
all so it's like there's so many variables that are at play here in
goodness.
terms of how fast runoff happens, and that's what we don't want. That's the I guess the takeaway is that we need to slow down and do what we can to slow down and stop runoff. This was one of those things they were talking about, like when rain hits a corn husk as opposed to hitting the soil itself, dramatic differences happen because of these micro impacts that are, it was a very intriguing article on how they're trying to mitigate flooding in the Missouri River Valley.
Yeah, interesting. Okay, that's very interesting. Yeah, that's an aspect I hadn't considered, like what the physics of the rain hitting the soil, really, and how it gets distributed there. So other things that people often do, we engineer these things. I'm going to move to image number 2 here real quick, is that we have retention ponds. We have a retention pond. You'll often see these in new developments, especially if there's a slope or if they're in a flash flood or really a rainfall prone area. Our neighborhood, like I mentioned, has one of these. We have basically there's like these, I don't know, call them swales or something, where, you know, on the hill slope we'll kind of have a trench that's dug that runs kind of at an angle down the hill, sort of a trench and then a hill. So you can kind of think of that. They're only a couple feet high, really. So that water flowing down the hill, if it's flowing as runoff down the hill face, will hit that little gully and it'll head off away from the houses, and then it'll dump into a retaining pond. And what happens when it goes to that retaining pond, it stops the water and allows it to soak into the soil more. So it'll slowly leave that retaining pond by soaking into the soil, which is also slowing down the water. And we're engineering these to get away from the infrastructure in many instances too.
And so they'll pick a low-lying area that's like inconsequential and like dig it deeper and so on. But they'll also, how do they slow it down? Well, it has a drain. So you have these inputs that come in, and then you have a drain, and they pack this drain in sand and gravel and rocks. So the water has to permeate through that before it can get to where it's going. So it dramatically slows it down. So during these events, the retention pond will fill up, hopefully not overflow, but fill up and then slowly drain out over time after the event has passed. But Jesse, you did skip over another cause before we skip to the ways that we mitigate these things, which is, what about climate change contributing to this too? Because, you know, storms are getting more severe. Droughts are more severe. Droughts lead to wildfires, which makes the soil impervious. It's like this vicious feedback loop, this positive feedback loop that climate change can create. And not to mention, and this is I think an amazing fact in geoscience and in climate science, is that just a 1 degree Celsius rise in temperature means that the air has a capacity to hold 7% more water vapor, moisture in the air. Wow. That's an amazing stat.
That's a lot. That's a lot more. So you can build, and this is Chris, this is one of the reasons why July in the United States, or sort of the end of June to early April, is called flash flood month by often people in the weather community, because basically hot air can hold more moisture, as you're saying, and these storm currents end up heading further north, and so they kind of get slower as they swing up into the north, and slower means slower storms holding more water in more water vapor in the storm cell will end up dumping a lot of rain in a slow moving storm, which means you get a lot more rain per unit area on the ground, because this is dumping a lot of rain. It's moving very slowly. So this is why summertime, in the Midwestern states, frequently are kind of a flash flood prone time in the West and Midwest in the United States, at least. So that's a really good point, Chris. So there's many things, right? We're doing the infrastructure, we're building all this impervious infrastructure, we're building houses, we're building developments, we're building roads, we're building parking lots, all those things. And we'll end by talking about some engineering things that can be done to alleviate. And basically, it is just say, instead of putting a pavement there, put something that will soak up the water or allow the water to get back into the groundwater. Really, with that, we have anthropogenic climate change. Those two paired things are creating potential for more and more catastrophic flash flood events. I think, Chris, the infrastructure one is worth just walking through because I think this shows another feature which is called lag time. And lag time for me, it just makes this whole flash flood event story make sense. So I'm going to turn to this image number 3 we have here, this GIF. And what we're going to show here, and you can imagine this if you can't see the image, you can just imagine this in your head. On the x-axis, we're just going to draw time starting from 0 and going forward in time. And on the y-axis is rainfall. And so what happens, we draw a rain event in there. So it starts sprinkling a little bit, and then the rain gets heavier and heavier and heavier, and it stays really heavy for, let's say, 5 hours, and then it starts to peter out. That's a rainfall event. So we got some peak there of rain. Now, what happens in a normal environment, so now let's picture an undeveloped field with forests and a big landscape like that, very natural, beautiful forest. When the rain hits,
Jesse's out in the field frolicking, gathering nuts and berries.
Frolicking around, that's right. Yep. Gathering nuts and berries and hugging some trees. And what happens when all this rain hits the landscape, right? It hits the leaves, it hits the grass, and it ends up, like you're saying, with the corn husk, it kind of gets broken apart and it ends up percolating down into the soil. And it percolates into the soil. Water in the soil eventually hits the groundwater table. It maybe raises the groundwater table a little bit, and that groundwater is flowing downslope at some level. So it's flowing slowly now in the soil downslope until it eventually makes its way into a stream, and then so the stream level rises and it moves down. And what we can then draw on this chart here is, with some time lag, we can draw the stream increasing after the rain event. It will increase its flow, and it'll have this long, broad hill where it increases slowly and it stays high for a little bit, and then it decreases slowly because all that water took a while to work its way through the system. And if we change this landscape in our mind, and let's say we have now a parking lot and a bunch of houses and a couple roads, and we're funneling all this stuff off into our gutter system, and that gutter system goes into the sewage system, and the sewage system has some outflow, and it's going into the drains, and the drains are just punching it right out into the stream, or a culvert that ends up going into a stream. Well, what happens when all that rain hits? It's all hitting the impervious surfaces at the same time. It's getting funneled really quickly into the culvert and then really quickly into the stream. So instead, after this kind of quote-unquote urbanization phenomenon, what we get is a really fast rise in that the same rainfall event would cause a really rapid rise in that same stream, and it would peak really high, and then it would come down a lot quicker. So our lag time gets a lot shorter, the lag between the peak in the rainfall and the peak in the stream gauge. So we can kind of measure, people measure these. They say, what is our rain gauge telling me versus what is my stream water gauge telling me? And so we can track these and track the lag time decreasing as a function of infrastructure being built, basically. That's not including different rainfall events. That's just saying the same rainfall event, if that occurs 5 years later, same rainfall event, it's probably going to have a shorter lag time because of development that's taken place. If we're doing development, which is what we do now, mostly with just impervious surfaces in a lot of different places, and no elegant approach to solving this problem. So I think that's interesting, an interesting way to track this, Chris. Like major stream, rainfall event, you have a rain gauge and a stream gauge, and you can really kind of simply work this out. Like how much urbanization, how much impervious surface is there in this stream catchment?
Absolutely.
I really like
it's a quantifiable thing, though, right?
Exactly.
Exactly. I do. I think you did a really good job with this, by the way. I had my doubts. I did have my doubts. Good job. Well done. It's such a simple, cheesy little hand-drawn diagram, but I love it. It does the job. It's so good.
But
this is a quantifiable thing.
That's the point. Like these are things. These are fun. We're not just saying, oh, flash floods. They happen.
Right.
And
it's not my opinion.
This is quantifiable. Like there's data to throw at this, and this is just a schematic version of that. So anyway,
that's right.
Yeah.
This is not conjecture. We're not being opinionated on this, saying, we're making this worse, we think. I mean, it's a thing. And so, mitigation is an interesting engineering problem, right?
Yeah,
you talked
totally.
about the retention ponds. What I love to do, Jesse, I live in an area. Our school is thriving. It's growing. We got, people want to move into this area. And so we built a newer school, a newer high school campus. It's huge. And I like to take my geoscience students outside on a nice day. I don't care what we're talking about. We can be talking about natural resources. We can be talking about plate tectonics or whatever. I'm going to take a nice day that's just beautiful, comfortable, and sunny, and let's go outside and let's do some geology in a ditch.
Oh, yeah.
And then let's go.
Geology in a ditch with Chris.
Yeah. There's so much you can see. But then,
Bring
let's
your trowel
look at
and your muck
let's
boots.
look at our whole. You're a piece of work. Let's look at everything though around this structure, and let's look at the human engineering and what we're doing.
Yeah, that's
and there are
good point.
probably I would say at least 7 big retention ponds in the area. All of these retention ponds are draining into this creek that runs right through the school. That we actually built a bridge over it, so the river runs underneath. But we have to slow this down. That's the responsible thing to do. And so that was a mitigation thing that we did right. And they're all over the place. I mean, it's not just a couple, it's there, and all new developments now have these, right? And then it's just students don't look at this and think about, oh, that's really cool. We have these retention ponds, they serve a purpose and it's an important function. It's a cool thing to be able to teach and point out that's relevant.
That is a really cool thing to do. And go this sort of geological engineering basically is what we're talking about, or environmental engineering, and it's a really powerful skill set and a really powerful example and case study to just go through and teach these really simple processes. And I'm sure you're standing there talking about infiltration and runoff and saying, why is this retention pond here? Work through this, like think about this. Look at the structure of it, like why is there that ravine right there that somebody's clearly dug? Like, what's going on? Why was that? Engineers put those there. Hydrologists evaluated, weighed in on where the engineers should put these things. Why did they do that? Right? Like, that's a really good example.
Really cool.
I like that.
Because we can go to a storm sewer, and I do this, and because I'm so old, Jesse. I don't do this myself, but I have one of my students. I'll say, hey, pick up that storm drain. Pick it up, the grate, and remove it. And we can look down in this. It's like a 3-foot diameter hole in the ground that's dug down, but you can see all the inputs coming from the rooftops, right? So you can see anywhere between 4 and 5 plastic PVC inputs into this drain. And then you can see one big output that goes straight to the retention pond. So you're able to pull that off, look at it, talk about it. Let's walk to the retention pond then. We can see the input coming in, and then we can see where the output, which is packed. It's a big mound in these retention ponds, like on one edge, that's packed in huge boulders, and then there'll be gravel and then sand around it all. Yeah, it's a neat, yeah. Yeah.
I like that. I like that a lot. That is very cool. I mean, these are just great things you just can discover so much just looking around you. I mean, I just found out, Chris, what was it? This weekend, I think, actually, talking to some neighbors that, I've been describing the sort of hydrology of my neighborhood a little bit. Well, this retention pond flows out into a stream, basically this little stream that sometimes has water in it, most of the time doesn't, sometimes a little trickle. But basically,
typical
that feeds
limestone area.
Yeah, exactly. That feeds into another stream that almost always has water in it, but that's a disappearing stream, and it disappears just down from our neighborhood. And then I also found out we have a sinkhole in our neighborhood. On one of the neighbors' properties, like a well-known little sinkhole area. And I looked at it on LiDAR after our conversation with Philip Prince. I now know exactly where to go to look at LiDAR. And you can see the dang thing on LiDAR. And you can see the retention pond. You can see all these little trenches that have been dug around to kind of funnel groundwater away. It's really cool to look at this LiDAR and link it to exactly what you're talking about, the story you can tell, and how these things have been engineered in these areas that are prone to flooding events, and water management is clearly a concern. So Anyway, I thought that was kind of interesting, linking LiDAR from our conversation with Philip Prince to, understand, we've talked about karst topography before. I live right on a limestone karsty area. So anyway, all very interesting. I figured you'd appreciate that, a little sinkhole.
I absolutely love that. Did you know about the disappearing stream when I was there?
No, I just found this out last weekend.
All right.
Talking to some neighbors.
Well, when I come out again, then I want to see this.
We'll do a field trip to my neighbor's house and look at the sinkhole too.
There we go.
Chris,
you
can stand in some karsty terrain.
Love it. I love to feel
That'd be
karsty.
pretty good, wouldn't it? And then I was looking at looking at it and like, wait, looking at the LiDAR, I was like, yeah, there's a ton of sinkholes. Like this person's got a sinkhole. There's another sinkhole back over there. Like it's totally fun. We could go exploring for sinkholes. Yeah.
Wow.
Really interesting, right?
That's really interesting. Because I wonder, there have to be sinkholes that are going to be problematic then.
Yeah, probably most likely. We are, and I realized, you're at our house, we have all this sandstone, like it's just kind of covering the ground, but we're actually on limestone, and the just up slope, there's a change in slope as you go just up from our house, and that's where the limestone transitions
towards the ridge
to the sandstone. So then yeah, exactly. And so all that stuff's just been sloughed off downhill. This is just soil creep bringing those sandstone boulders that are in our yard downhill. But if you dig down, we're in the limestone. So interesting, right?
That is really cool. We could do a geology field trip in an episode right in your backyard.
Right in your backyard. How good would that be?
Yeah.
That'd be awesome. Yeah.
We could
go check out the retaining
We could do some
pond.
biology and include the snakes.
Include the snakes in the tree. It'd be great, man. I mean, it's just the full naturalist experience over here in Pennsylvania. Totally great.
Good stuff.
Oh man, well I hope we didn't make light of any of these events. Flash floods are dangerous, deadly, and they're not to be trifled with, but I think the understanding and sort of the geology behind them is interesting and important for people to know, frankly. Like this is important stuff to know and to consider, and so think about the alternatives and pay attention to the alternative technologies that are out there for engineering around these problems and increase infiltration. Maybe that's a shirt.
Mm-hmm.
We need more infiltration in our world.
That's such a good idea. That is a good idea. I'm going to do that.
What are you going to call it? You're better at naming on shirts than I am. What's it going to be?
Increase the infiltration. That's it.
I love it. There we go. All right, done.
Yeah.
You know what?
With
Send
maybe
text
some
this to my
arrows
wife.
pointing down, some little squirrely arrows.
That'd be great, actually.
Yeah,
I love that.
I know.
Increase infiltration. Yeah. All right, done.
Right.
I like that. There we go. It's kind of bridges the environmental
engineering.
You and I. Yeah, there we go. I like this. Okay, hey, that would be good. We'll give this to my wife, and she'll mock something up and put it on the Planet Geo website shop, so you can find stuff there.
Yeah, that's perfect. Love it.
Excellent.
Hey, the one thing that we did not talk about that is really cool, and my alma mater, Grand Valley, does a really good job of this, which is trying to create porous and permeable asphalt and concrete along the perimeters of parking lots and buildings and so on, which does a really, really good job of allowing the water to infiltrate before it gets to the storm sewers, which is why they put it on the perimeters. Let's say you set up a perimeter of 10 to 20 feet before it gets those storm sewers. It allows it to get into the ground, permeate in, and then just take its natural course to where it's going, and it dramatically slows down. So this stuff is expensive, almost twice as much as regular asphalt and concrete, but it does its job, and that's another way to mitigate this kind of thing.
Increase infiltration. Yeah. Increase infiltration, man. There we go. Love it.
That's a shirt.
Hey, this episode will very soon, if not already, be on our CampGeo mobile app. We are making a streams chapter that this will be a part of in our main CampGeo content there. So check it out. We've got a new revised version of the app that'll be up here soon with some new updates coming your way. You can follow us on all the social medias. We're at Planet Geocast. Send us an email. There's a contact us link at our website, planetgeocast.com. And we love to hear from you. We like doing our listener question episode, and we're hoping to do more of those in the future. So please hit us up with any questions you have.
Cheers.
Peace.